You know, there's a hidden arms race happening as we speak. Not on some dusty battlefield, but inside the secure digital connections we all rely on every single second. It's a high-stakes race to build a brand new kind of lock before a radical new kind of key can come along and break everything wide open. Just think about that for a second. Every single email, every bank transfer, every government secret, poof, suddenly out in the open. It sounds like something straight out of a movie, but it's a very real future that cryptographers are working around the clock to prevent. The master key in this story is a quantum computer, and today we're going to break it all down. What the threat actually is, how our current security even works, and most importantly, what the world's brightest minds are doing right now to keep our digital lives from falling apart. All right, so first things first, we need to get our heads around the tool that could change, well, pretty much everything. What is a quantum computer anyway? Here's a simple way to picture it. A normal computer trying to crack a code is like someone trying every key on a giant keychain, one by one by one. It's tedious. A quantum computer, on the other hand, uses the bizarre, mind-bending rules of quantum mechanics to essentially try all the keys at the exact same time. It's a computational superpower, but only for very specific kinds of problems. And here's the kicker. One of those specific problems it's amazing at is the exact kind of math that protects the entire internet. This is where the threat gets very, very real. I mean, just look at this. We're talking about cracking a super common encryption standard, RSA 2048, in less than 10 hours. Or another one, ECC 256, in under 6. These are problems that would take our best supercomputers today literally billions of years to solve. A quantum computer could do it before you're done with your workday. So, to really understand how this new key works, we first have to take a look at the lock it's designed to pick. Let's break down the digital fortress we all use every single day, whether we realize it or not. You know that little padlock icon up in your browser's address bar? We see it all the time. Well, that little symbol is just the tip of a massive, incredibly complex iceberg. Every time it appears, your browser and the website's server are doing this intricate digital dance, a greeting called a TLS handshake, to create a totally private and secure tunnel just for you. This whole handshake thing really boils down to two things: trust and secrecy. First, your browser needs to be absolutely sure the website is who it claims to be. That's the trust part, authentication. Then, they need to secretly agree on a special code, a shared key that only they know. For this crucial first step, they use something called asymmetric encryption. It's like having a public mailbox where anyone can drop a message in, but only you have the private key to open it up. Okay, so once that secret key is safely exchanged, the heavy lifting begins. All your actual data, your password, your credit card number, all of it gets encrypted using a different, much faster method called symmetric encryption. In this case, the same secret key is used to both lock and unlock the information. And the global gold standard for this is an algorithm called AES. It is the workhorse of internet security, and it's been the bedrock of our safety online for decades. So, we have two main phases, right? The asymmetric handshake to create the secret key, and the symmetric encryption to actually use that key. Now that we know how the lock is built, let's look at the quantum keys designed to smash it to pieces. And this is basically a two-pronged attack. First up is Shor's algorithm. Think of this as the ultimate master lockpick. It's specifically designed to crack the complex math behind that initial key exchange, allowing a quantum computer to just figure out the secret key. Then you have Grover's algorithm. This one is less of a lockpick and more of a battering ram. It makes brute force guessing attacks on symmetric encryption like AES way, way faster, which basically weakens the whole system. I mean, just let that sink in for a moment. The word here isn't weakened or compromised, it's useless. That's the scale of what we're talking about. The very foundation of trust on the internet could just crumble. Okay, so that all sounds pretty dire. But the story absolutely does not end there. Knowing this storm was on the horizon, the world's cryptographers have been working for years to build a much stronger shelter. Welcome to the new frontier of cybersecurity, post-quantum cryptography, or PQC. The goal here is pretty simple in concept: create entirely new kinds of encryption based on math problems that are incredibly hard for both our normal computers and for quantum computers to solve. And this isn't just some chaotic free-for-all. The U.S. National Institute of Standards and Technology, NIST, has been orchestrating a massive global competition since 2016. They've invited experts from all over the world to submit their best ideas, and then they've spent years rigorously testing, analyzing, and trying to break them, all to find the absolute best replacements. Now, the challenge is that there's no single perfect solution that's best for everything. It's all a game of trade-offs. Some of these new quantum-proof algorithms are incredibly fast, but they have really big key sizes. Others are more compact, but maybe a little slower. It's a balancing act. So the crucial takeaway here is that the future of encryption won't be one size fits all. You'll have algorithms like Crystal's Kyber, which is fast and has a pretty small key size, making it perfect for high-frequency stuff like financial transactions. But then you'll have something like Sphinx Plus, which is a bit bulkier but incredibly robust, making it great for things you need to keep secure for decades, like healthcare records. But after all those years of evaluation, NIST has picked a clear frontrunner for general everyday use. An algorithm called Crystal's Kyber has emerged as the leading candidate because it just hits that sweet spot of strong security, manageable size, and high efficiency. It's ready for prime time. So how in the world do you upgrade the entire internet without everything just breaking? The answer is really clever, a hybrid approach. For a while, systems will run both the old, trusted encryption we use today and a new quantum-resistant one side by side. It's kind of like wearing a belt and suspenders. You're secure against today's threats, and you're fully prepared for tomorrow's. And that's really the most important thing to understand here. While the threat is monumental, the solution isn't some far-off dream. It's already being rolled out. This isn't a panic button moment. It's a massive, coordinated, and proactive engineering project that's happening right now, quietly behind the scenes. So the next time you're browsing online and you see that familiar little padlock, maybe take a second. Because behind that simple icon is an incredible story of digital fortresses, universe-bending quantum keys, and a silent global race to keep all of our futures secure.